So welcome back, everyone. Our next speaker is Elvey Price, and he's going to tell us about enumeration of walks with small steps avoiding a quadrant. Go ahead, Andrew.
Okay, thank you. And thanks to all the organizers for giving me the opportunity to speak at this conference. This is a specific version of a more general question, which is that of walks in cones. So the idea for walks in cones is that we take some step set, some finite subset of z squared, and we take a cone in r squared, such as this one, and a starting point, which I'll always denote by the blue square. And we want to count the number of walks using this step set, starting at the blue square, and so of each length and ending at each point. So if we let Cijn be the number of such paths, so ending at ij and of length n, then we want to determine these numbers, or equivalently, we want to determine the generating function, which is the series with these numbers as coefficients. Okay, so the simplest version of this question is where the cone is the entire plane. And so in this case, we just get simple rational series such as this for the generating function. The sort of next simplest case is the half plane, in which case it's proven that we always get algebraic series. And so as it turns out, there are really only two remaining cases for cones in the plane. So the first case is where we get a convex cone, which can be deformed to a quarter plane. And so really any such question in a convex cone is equivalent to another question in the quarter plane. And then the other case is where we have a non-convex cone, which can be deformed to the three-quarter plane. Okay, so for the quarter plane case, the solutions are now very well understood. Mireille Bousquet-Mellu and Marnie Mishna showed that there are 79 different non-trivial step sets we could choose, sort of small step sets we could choose. So if we only allow nearest neighbor and diagonal steps. And so in all 79 cases, these are solved in terms of integral expressions. Integral-free solutions have been found in 32 cases. And in some sense, it's been shown that in the remaining 47 cases, no such solution exists. So these are now very well understood. This involved a very large number of papers by all of these different authors. And so in this work, I show that more or less the same thing happens in the three-quarter plane. So for the three-quarter plane, we're always going to start the walks at 1, 1, at least to start with. And so, to reiterate, we want to determine this generating function, which counts walks with x counting the final x coordinate of the walk, y counting the final y coordinate, and t counting the length of the walk. Okay, so I said that more or less the same thing happens. So the main counterexample to that is that there are these 5 step sets which do interesting things in the quarter plane, but which do very uninteresting things in the three-quarter plane. And so there are really only 74 remaining interesting cases. But yeah, so for those 74 remaining cases, the solution in each case is somewhat similar to the solution in the quarter plane, as I'll sort of show. So previously, previously there were solutions for this problem for 14 different sets of varying levels of specificity. And so I've sort of drawn so these were proven between 7 different papers, and so for each of these articles, I've drawn which step sets the article applies to. But yeah, so previously 14 cases had been more or less solved, and so this work solves the remaining 60 cases and also these 14 cases, admittedly a bit less explicitly than some of these. Okay. So for the outline of this talk, for the first part, I'll describe how we can derive a functional equation which characterizes the generating function that we're interested in. For the second part, the second part is sort of the new bit, which is the conversion of this formal functional equation that relates to formal power series to an analytic functional equation that relates to meromorphic functions in the complex plane. And so this is probably going to be a bit abstract because I'm not going to define all of the functions involved. But so in the last part, I'll describe a specific example where we get much simpler solutions. And so then at the end, I'll define everything. I'll give some results where everything is defined. Okay. So yeah, so to derive a functional equation, so to start with, I'm going to call the walks that we're interested in cone walks. So cone walks will be the ones that don't touch the boundary at all. And so then to derive a functional equation, I need to define something which I'll call dead walks. And the concept being that if our walker accidentally walks into the boundary, he instantly dies. And so dead walks will be walks where our walker has died, so they touch the boundary only at their final step. Okay, and so we can get a functional equation relating cone walks, which are the walks we're interested in, to dead walks using this combinatorial decomposition. So the idea is that if we take a cone walk and then if we take a cone walk and add a single step, then either will still be a cone walk because we didn't crash into the boundary, or our walker will crash into the boundary and we'll get a dead walk. And so this combinatorial decomposition converts directly to a functional equation relating C, the generating function for cone walks, to D, the generating function for dead walks. And yeah, here P is a polynomial that just represents a single step in the walk. So it's just based on the step set. Okay, and so the reason why this is useful is that we know something else about D, which is that it splits as a function of x plus just a function of y. So where the function of x comes from walks that end in this region A, which is the non-positive x-axis, and the function b comes from walks that end on the negative y-axis. And so A doesn't involve y and b doesn't involve x. Okay, so now we can simplify this equation a bit by writing the kernel, which will allow us to collect all of the terms involving C. And then, so just taking this equation, collecting the terms involving C, and then splitting D as A plus B, we get this equation. And so we want to solve this equation for C, A, and B. And it turns out that the three series are uniquely defined by this equation, given that we know where they have non-zero coefficients. Okay, so that's the formal functional equation. So now for part 2, where I'll describe the converting this to an analytic functional equation. And so this was done in the quarter plane by Kilian Raschel based on methods used in a more probabilistic setting by Fayol, Ionegorodsky, and Melishev. And so the results of this section in the quarter plane have been used in all of these articles to derive different results. And so similarly, this result in the 3/4 plane can be used to derive similar results for the 3/4 plane. Okay, so so we start with the functional equation, the formal functional equation that I derived in the last section. And so the idea for solving this, or for converting it to an analytic functional equation, is we start by fixing t to be very small, so that hopefully some of these series will converge. And then we define meromorphic functions x and y, which will in fact be elliptic functions, so that they send the kernel to 0. Okay, and so then the point of this is that, right, and so these functions are based on t as well. So the point of this is that if we then substitute x to x of z and y to y of z into this equation, then it will cancel out the complicated bit involving c. And so we'll get this equation that, well, in some sense is simpler. But unfortunately, this only works if c converges. And in our case, c will pretty much never converge. So in the quarter plane case, this is immediately what we need to do because c would converge, but in our case, in certain cases, for certain values of z. The problem is here that c has both positive and negative powers of both x and y, because the walk could finish anywhere. And so when we try to plug this in, either x is going to be too big for it to converge, or x will be too small for it to converge, or y will be too big for it to converge, or y will be too small for it to converge. And so we can't quite do this directly. So to get around this problem, we split the 3/4 plane into 3 quarter planes. And in doing so, this splits our generating function into the sum of 3 generating functions, where each of these generating functions counts the walks counted by c, that is, it counts cone walks, so just walks avoiding the red line, but they each count those walks which finish in a specific one of these 3 quarter planes. So obviously q-1 counts the walks that end in this region, q-1, q0 counts the walks that end in this region, and q1 counts the walks ending in this region. Okay, and so, so as I said, this splits our counting function. So I've just removed t as a variable because otherwise the things won't fit on the page, and t is constant at this point anyway. But yeah, so this, so as I said, we've split c into 3 pieces. And in fact, this splits the equation itself into 3 equations, which look a bit more complicated, but that's not a problem. But importantly, these equations, or all of the series in these equations, in each of these equations, do converge in a useful region. So because this equation only involves positive powers of x and negative powers of y, and we chose t sufficiently small, it will converge as long as x is small and y is big. Okay, so now we can substitute x to x of z and y to y of z, where x of z and y of z are these elliptic functions that send the kernel to 0. And so we substitute this into the top equation and the bottom equation. And yeah, so then this new equation will hold for Z in a certain region, satisfying this inequality. Now, conveniently, the complex plane splits very nicely based on whether X of Z and Y of Z satisfy inequalities of that form. So for example, yeah, so it splits into infinitely many strips where here omega 0 is the strip where X of Z and Y of Z are both less than 1. Omega 1 is a strip where Y of Z is less than 1 and X of Z is greater than 1, and so on. And these strips will repeat every 4 times you go up, because X of Z and Y of Z have pi tau as a period. Okay, but so what all this means is that our equation will hold for Z in a particular one of these regions. So we can choose Z in omega 1, omega minus 1, because in that region, this inequality holds. Similarly, the bottom equation will hold for Z in omega 1. Okay, so now it's convenient to think of these functions now as functions directly of Z. So that is, we define this function of Z as the thing that appears here, and similarly H hat, V hat, and A hat of Z. And again, these are going to be defined in specific pairs of these regions, because now for this to converge, we only need YZ to be greater than 1, and it doesn't matter what XZ is. Okay, so now after making these definitions, our equations simplify significantly. And so doing all the same things to the middle equation as we did to these, so substituting in X to X of Z, Y to Y of Z, and then converting to these functions, this becomes this simple equation. Okay, so now we have these 3 equations to solve, where we've defined these complicated things. But it turns out that we can prove that using these equations, that B hat, H hat, V hat, and A hat extend to meromorphic functions on all of C. So even though these are only defined in certain regions, they meromorphically extend to the entire complex plane. Okay, and so that means that since these equations hold in certain regions, they must actually hold on all of C. So we can compare them directly. In particular, we can just add up these 3 equations, and we get this simple looking equation. So to summarize, we've defined B hat and A hat using the series A and B, which we're counting dead walks in certain regions. And so we've defined A hat and B hat on completely non-intersecting regions. But then the meromorphic extensions can be compared directly. Okay, and so this functional equation isn't enough by itself to determine A hat and B hat uniquely, but just from the definitions, we get a number of other properties satisfied by A hat and B hat. And together with these properties, this equation does define the functions, does uniquely define the functions, and therefore it uniquely defines the series A and B, and hence from the formal functional equation, it defines the series C that we were interested in. Okay, so yeah, and so this is very similar to the functional equation that occurs in the quarter plane case that was derived by Killian Raschel. The only difference being that, yeah, here we have a gamma instead of a pi tau minus gamma, and similarly here, well, yeah. But so it's very similar, and so this is why it leads to the same sorts of solutions. in particular, for example, we get explicit integral expression solutions, as shown here, where, okay, I haven't defined omega either, but so each of x, y, and omega is an explicit elliptic function. That's, albeit explicit, it's slightly too complicated to define on one or two slides. Okay, so finally, I'll describe the cases where we get simpler results, I guess more concrete results. So yeah, so in this case, rather than starting at 1, 1, so rather than starting here, we start somewhere on the x-axis. Okay, so in particular, if you start at 1, 0, then the equation we need to solve, instead of being xz, yz equals a sum of a and b, it's just x of z equals something like a of z plus b of z. And so this is nice because, well, so a1 and b1 satisfy these symmetry relations. And so this is always the case for a and b. And so, and x satisfies the same relations as a. Sort of the reason why a satisfies these relations, because it's defined using x. Okay, and so then if we rearrange this, we write b1 is x of z minus a1 of z, then b1 has to also satisfy the symmetry relations of a1. Okay, so b1 satisfies all of these relations, which if you sort of compare, well, if you compare these two, it means that b1 has pi as a period, and if you compare these two, it means that b1 has 2 pi tau minus 2 gamma as a period. So it's an elliptic function, which means we can solve it. And in fact, it's precisely the this elliptic function where omega was the function I described on the previous slide for the integral expressions. Okay, and we can do the same thing if we start at a point p0. So in that case, we'd get xz to the p here, but still we get that b1, bp now is an elliptic function. And in fact, it will be a degree polynomial, a degree p polynomial of b1. Okay, so that's still in the analytic world, but now using this polynomial, we can move back to the formal power series world, and we can, and so this implies that we can write the series AP and BP that just count walks ending on the axes starting at, so they count dead walks that start on the axes and end at, end on the negative axes. And so, yeah, moving back to this power, formal power series world, these are simply related to A1 and B1, so they can be written directly in terms of these. In particular, even just for p equals 2, we get this surprising result. So this result is, we consider walks starting, so we take any step set, we consider walks starting at 2, 0, ending at -1, 0, which only touch the red line at their final point. And it turns out that the result on the last page implies that exactly half of these walks will pass through this green line. And so, yeah, to see the relationship with the last page, the walks that don't touch the green line are essentially walks from 1, 0 to -2, 0, in a sense. Okay, and we can do all the same things where we put weights on the steps, and somehow this implies that the inequality, this equality even holds if we require that the walks have a specific number of each type of step. So yeah, so it would be nice to have a bijection of this. So just as an example of this result, if we take walks that use exactly 1 down step, 2 northwest steps, and 1 southwest step, then exactly, well, there are 4 such walks. and exactly 2 of them touch the green line. Okay, so that's all. Thank you for your attention.
Thank you. Are there any questions for the speaker? Yes.
Hello. Yeah, I was just wondering how hard it is to change the starting point. How much does the behavior depend on that?
Okay, so okay, let's just go back to where I have this equation. So if you change the starting point from something like 1, 1, yeah, so initially it was 1, 1. So if you change it to something like PQ, this equation will just change to x. You'll just get x of z to the p times y of z to the q in this equation. So yeah, so the behavior can change, but yeah, it's a good question. So the behavior can change in certain ways, but not in every way. So I didn't really describe what algebraic and D-algebraic and D-finite mean, but if you know what those are, then in the end, whether the generating function is D-finite doesn't depend on the starting point, but if it's algebraic or D-algebraic can depend on the starting point. And so sort of why things could be simpler when we start on the x-axis.
Thanks.
Any other questions? Oh, yes, over there.
Yeah, so there are many other walks that you can consider and also many other cones other than the quarter or three-quarter plane. But is there some beginnings of a general theory that you could, if I give you some angle for the quarter plane and some walk, can you predict what type it will be, whether it will be well behaved or not?
So yeah, so I sort of skipped over. So I mean, I made the claim that in some sense any convex cone will be equivalent to the quarter plane, but of course that will change the step set. So I guess the question is, if you take a nice step set with some funny angle, then yeah, then it becomes more complicated. Essentially, so the answer is possibly no. I don't know what to do, and so the problem is, if you can have steps that could jump over one of the axes, then this method won't work, at least not immediately. So is that
So I think the thing that I might hope for is that there would be some way to say in advance whether one of those will be, for example, D-finite or D-algebraic.
Right.
Even if you can solve and say exactly what it is.
Yeah, so I don't know. I mean, I guess yeah, it would be nice to know in some general cases, if things work out nicely like that. I suppose in some sense, my intuition is that if there isn't a reason why it is going to be nice, then it just won't be the algebraic. But I think, yeah, people have considered some of these things. So for example, if you take, I mean, I think it's equivalent to considering walks with larger steps, which is very difficult.
Thank you.
Yes.
So have you considered walks confined between two parallel lines?
I haven't. I'm sure people have considered this, but yeah.
Okay, thanks.
So I think, yeah.
Any other questions?
So I want to ask, so once you've gotten these functional equations, how difficult is the classification of the generating functions into the different classes after this? And do you rely on the classification that's already been done for the quarter plane and half plane cases?
Yes, so we rely on the methods. So I would say if you perfectly understand all of okay, I thought this would be faster to find all of the, I guess, okay, it's somewhere here. Yeah. So if you perfectly understand all of these papers that related to walks in the quarter plane, then it's quite easy to use the same methods for this functional equation. So it doesn't immediately rely, well, it relies on some results that are general in those, but it doesn't, yeah, it's essentially using the same methods as they used on the new, slightly different functional equation, but it's so similar that the same classification more or less works, at least in the cases where they've applied these results to those functional equations. So actually, in my work, I've only classified them as functions of x, and then if you try to do it as functions of t, then it doesn't work so immediately. But yeah.
Thank you.
Good question.
Yes. Anyone else? Okay, so let's thank the speaker again.